There's a parcel of land just outside Guelph in southwestern Ontario that stopped being an active farm more than a decade before anyone thought to install photovoltaic panels on it. It sits on research acreage between two regional concession roads, and for years its management was reduced to a single annual chore. A contractor drove a tractor with a rotary brush cutter across it once every autumn. That was the entire relationship between human stewardship and that soil. The goal was merely to beat back the woody brush and goldenrod so the acreage did not revert to scrub woodland, while otherwise leaving it completely abandoned to its own devices. Land like this is not rare. It is one of the most familiar rural landscapes across southern Ontario, the St. Lawrence lowlands, and the fringes of the prairies, yet we scarcely have an adequate name for it. It is not working cropland, not mature forest, not native tallgrass prairie. It is simply leftover space. Ground that was once cleared and tiled for the plow, eventually deemed marginal or uneconomic, and now lingers in an administrative gray zone. Mown just frequently enough to meet municipal property standards and avoid noxious weed citations, but never cultivated deliberately enough to sustain a living ecosystem. In 2019, the steel posts and racking arrived. 22 hectares of ground-mounted solar arrays divided into 5 separately fenced utility blocks. If you had driven past that perimeter fence along the concession line that summer, you would have seen the standard portrait of modern renewable infrastructure. Endless ranks of dark monocrystalline glass angled toward the southern sky, crushed gravel access lanes, inverter housings, and chain-link security fencing topped with warning placards. It carried the sterile visual aesthetic of heavy electrical utilities, the visual language of a place where nothing is meant to live. Then researchers introduced a flock of sheep. And then, crucially, they started taking rigorous measurements. I want to explore what happens when researchers and agronomists take the ecological questions seriously on ground that conventional planning had already written off. The data gathered over subsequent seasons across Canadian test plots and comparable regional installations offers findings that are deeply counterintuitive. The results defy the standard assumptions held by both renewable developers and conservationists. But we must examine these findings with clear-eyed precision, because this subject is frequently obscured by superficial green energy marketing. There is a narrative circulating that presents this as an effortless pastoral triumph without examining the underlying arithmetic. The actual ecological mechanisms are far more complex, economically nuanced, and biologically fascinating. Consider first the sheer geographic scale, because scale transforms this from an agronomic novelty into an urgent land use issue. Natural Resources Canada and provincial grid operators have modeled what it will take to achieve a net zero national electricity grid by 2050. Delivering that clean capacity will require tens of thousands of hectares of ground-mounted solar generation across the country. We are not discussing urban rooftop arrays. We are discussing extensive ground footprint. A significant portion of this future development is slated for Class 1, 2, and 3 agricultural soils across southern Alberta, Saskatchewan, and rural Ontario. Prime agricultural land is naturally flat, already cleared of heavy timber, conveniently situated near transmission corridors, and held by landowners navigating tight farm margins. The expansion is already underway, with utility-scale capacity steadily climbing across provincial jurisdictions. The fundamental policy question is what these fenced tracts of land will become once the high-voltage lines are energized. For the initial decades of utility-scale development, the default industry protocol was straightforward. Plant whatever low-cost commercial turf mix was easiest to control, and keep it suppressed using heavy diesel mowers or broadleaf herbicides. On an operating solar facility, living vegetation is treated not as an ecological asset, but as an operational liability. If forage grows tall enough to cast shadows across the bottom row of photovoltaic cells, it directly degrades power output and revenue, so it is chopped back. This mechanical reality opened the door to targeted multi-species grazing, fundamentally reshaping how rural infrastructure integrates into working agricultural landscapes. The practice of targeted solar grazing across Canada has evolved from a marginal pilot concept into an established agricultural discipline. Over the past several years, commercial sheep flocks have been deployed across dozens of utility-scale photovoltaic installations, from the sunny plateaus of southern Alberta to the agricultural corridors of southwestern Ontario. What makes this burgeoning agrivoltaic sector particularly noteworthy is its demographic profile. More than a third of solar grazing flock managers are women, representing a remarkably high proportion compared to conventional livestock farming. Furthermore, the average age of these operators is significantly younger than the broader Canadian agricultural average, where the median producer age continues to climb past 55. Nearly 9 in 10 arrived at these renewable energy partnerships with substantial commercial livestock management and flock husbandry experience already established. This is neither a novelty nor an amateur pastoral hobby. It is an organized, entrepreneurial agricultural sector that has emerged largely within the last decade. To understand the underlying science, we have to return to that controlled research ground outside Guelph. The experimental program was launched not merely to demonstrate whether sheep could keep grass short, but to conduct an instrumented, long-term ecological investigation. Each of the fenced solar blocks was treated as a distinct experimental unit, testing 6 distinct operational regimes. An ungrazed control parcel, maintained strictly through mechanical mowing, alongside stratified stocking rates ranging from light, intermittent grazing up to high-density stocking of 20 to 50 sheep per hectare. The trial flock drew on robust domestic genetics, well-suited to the regional climate, including Rideau-Arcot, Dorset, and East Frisian crosses. Surrounding the animal scientists was a dedicated multidisciplinary research team, soil biogeochemists tracking active organic carbon and nutrient cycling, plant ecologists mapping botanical composition, and field entomologists methodically surveying beneficial insects, native bees, and predatory beetles. The early empirical data revealed an operational principle that seasoned shepherds understand intuitively, but which utility engineers had never quantified. Moderate stocking, roughly 20 sheep per hectare, yielded the single best ecological and operational outcome. Neither the heaviest stocking density nor the completely ungrazed mechanical baseline achieved optimal results. Under this moderate rotational regime, the ground sustained a rich cover of blooming forbs, clover, and wild legumes alongside active insect communities, while still cropping the vegetation low enough that it never cast shadows across the bottom edge of the photovoltaic modules. Ladybug populations averaged approximately 1 insect per 6 square meters across both adult and larval stages, proving that these predatory beetles were actively breeding and completing life cycles inside the perimeter rather than merely passing through. Most significantly, taxonomists identified multiple uncommon native bee species, establishing nesting territory beneath the modules. Inside an industrial energy facility, bounded by security fencing, native wild pollinators were taking up permanent residence. To establish whether this was a regional fluke or a repeatable biological pattern, researchers turned to multi-year comparative trials conducted across northern agricultural zones on decommissioned cropland. At large utility facilities where native prairie grasses and perennial wildflowers were deliberately seeded into the post-agricultural soil rather than standard turf, scientists conducted hundreds of standardized transect surveys across 5 consecutive growing seasons. Every single biodiversity indicator moved upward: floral richness, flowering plant diversity, total insect biomass, and native pollinator counts. Total insect abundance tripled, while native bee populations expanded 20-fold over the course of the study. The system was driven by working generalists, primarily goldenrod soldier beetles and hoverflies. Crucially, the researchers documented an unexpected ecological dividend. These expanding insect populations did not remain enclosed within the perimeter fence. They regularly dispersed into adjacent commercial soybean and canola fields, providing free, measurable pollination services to surrounding working farms. This is precisely where the conventional marketing narrative often halts. Sheep plus solar modules yields instant biodiversity, and everyone wins. But when we examine the precise underlying mechanics, The popular version has the ecological causation almost entirely backward. The sheep are not magically generating this ecological surge. The dramatic rise in insect life observed across these research sites was fundamentally driven by the deliberate establishment of native tallgrass prairie and meadow species seeded directly into the soil at commissioning. The steady surge in pollinator density tracked the natural biological maturation of that intentional botanical restoration. What the data captured was a calculated ecological revegetation project that happened to host steel solar racking, not an industrial facility that spontaneously generated biodiversity on its own. Furthermore, we must examine the baseline against which these gains are measured. Nearly all of these installations were constructed on land previously subjected to intensive, continuous row crop agriculture, decades of monocropped corn, soybeans, or wheat treated with routine chemical applications. Measuring a 20-fold jump in native pollinators sounds miraculous until one acknowledges the barren ecological starting point of depleted, herbicide-treated topsoil. Researchers have been transparent about this comparative limitation. These utility sites were contrasted against chemically maintained field crops rather than permanent provincial conservation reserves or pristine native grassland. We know with certainty that managed agrivoltaic ground is vastly superior to bare, intensive tillage. Whether it matches an undisturbed, long-term native meadow restoration remains an open scientific question that requires honest evaluation. Yet there is a second, highly distinct physical mechanism at work within these arrays, and it belongs entirely to the engineering of the photovoltaic hardware rather than the livestock or the seed mix. A utility-scale solar array fundamentally alters the local microclimate beneath it. Multi-year atmospheric and soil sensors deployed beneath Canadian panels and surrounding open ground demonstrate marked, repeatable variations in temperature, solar irradiance, and moisture retention. The ground directly beneath the racking experiences shaded, significantly cooled soil and air temperatures, muted diurnal heat spikes during midsummer heat waves, and reduced evaporative moisture loss. Simultaneously, the angled glass surfaces alter precipitation patterns across the field. Rainfall does not descend uniformly across the soil surface. Instead, precipitation sheets across the tilted glass and cascades from the lower drip line. This concentrated runoff carves a wetter, deeply watered band directly beneath the lower module edge, while creating a sheltered, drier rain shadow strip beneath the upper structure. An operational photovoltaic array is therefore not a uniform landscape, but a repeating microclimatic mosaic of 3 or 4 distinct environmental microzones, tiled across dozens of hectares with sharp transitions between them. In ecology, structured microclimatic mosaics naturally drive plant diversity and structural niche differentiation. Agronomic forage sampling across commercial sites has quantified the direct biochemical consequences of this physical reality. Exclusion cages placed in shaded zones beneath the panels versus open rows between the racking revealed that forage growing in shaded microclimates contains significantly higher crude protein concentrations, averaging 19.5% compared to 14.5% in full sun, alongside lower structural fiber and higher digestibility. The artificial shade created a richer, more nutrient-dense feed for grazing livestock. But this nutritional advantage came with an unavoidable trade-off. Total dry matter yield beneath the panels was roughly 1/3 lower than in the unshaded intervals. Higher feed quality balanced against reduced total volume represents the true thermodynamic bargain forged between the steel racking and the underlying soil. If the photovoltaic modules and the initial botanical seed mixes are performing the foundational ecological work, what specific role do the grazing livestock fulfill? The answer comes down to 2 distinct functions, both of which are far more sophisticated than simply acting as biological lawnmowers. The first is that grazing animals perform physical and biological soil work that machinery simply cannot duplicate. As sheep rotate methodically across a solar parcel, their hoof action continuously presses manure, urine, shed seed heads, and decaying plant litter directly into the upper soil surface. Unlike the violent, singular pass of a mechanical tractor deck, this animal disturbance is continuous, gentle, and biologically active. Comparative soil testing confirms the tangible benefits. Grazed agrivoltaic soils develop significantly higher organic matter levels, averaging roughly 4.5% compared to 3.5% on ungrazed control land. Furthermore, grazed parcels display markedly elevated active carbon pools, surpassing 600 parts per million, alongside enhanced soil protein indices and balanced pH levels that sit closer to the agronomic optimum. The second function is more strategic, addressing the long-term stewardship of the Canadian agricultural land base. Ground-mounted solar lease agreements are not permanent land conversions. They are typically contracted for 25 to 40 years. When these facilities reach their end of life and are decommissioned, the vital question is whether the underlying ground can seamlessly transition back into high-yield food production. Rotational solar grazing ensures the acreage maintains its functional identity as working pasture throughout the entire operational lifespan of the energy project. It keeps the biological microbial networks alive, maintains an established root sward, prevents severe compaction, and preserves the agricultural integrity of the soil rather than letting it degrade into an industrial brownfield requiring intensive remediation. Yet we must confront the significant logistical and financial complications, because an environmental thesis that ignores harsh economic reality cannot stand up to scrutiny. The first complication is financial. The popular assumption that grazing livestock is inherently cheaper than commercial tractor mowing is demonstrably inaccurate. When researchers costed the full enterprise, the upfront capital expenditure of mobile handling pens, fencing, transport, and water infrastructure pushed the first-year grazing expense to well over $2,000 per hectare. Even when amortized over a 10 to 15-year service contract, specialized grazing management leveled out near $900 to $950 per hectare annually, still somewhat higher than straightforward commercial mowing contracts. Achieving parity depends entirely on long-term contractual certainty and site-specific infrastructure. Graziers operating under volatile, short-term utility agreements frequently face site access restrictions, operational bottlenecks, and the heavy financial penalty of hauling thousands of liters of livestock water to arid, unserviced rural parcels. In Canadian rural settings, operators must also budget for livestock guardian dogs to protect flocks from coyote predation along extensive perimeter lines. The second complication concerns soil dynamics and data limitations. While grazed acreage outperformed neglected turf over time, multi-year trials demonstrated that short-term soil aggregate stability, the physical ability of soil crumbs to resist erosion during extreme rainfall, actually experienced measurable drops during seasons marked by severe regional droughts, followed by torrential precipitation. Furthermore, several surveyed sites exhibited legacy soil phosphorus accumulations exceeding 100 parts per million, creating genuine nutrient runoff vulnerabilities into regional watersheds and provincial drainage basins. Moreover, because long-term soil carbon sequestration often takes a decade or more to register statistically, current datasets represent an essential scientific baseline rather than a definitive long-term verdict. Finally, we must recognize that solar construction itself involves heavy topsoil grading and compaction that causes initial ecological damage. You cannot celebrate post-construction recovery without acknowledging the mechanical disruption that necessitated that recovery in the first place. Nor does agrivoltaics entirely erase the contentious political debate surrounding renewable energy siting on prime Class 1 and Class 2 farmland across rural municipalities. Ultimately, this is not a romantic story of spontaneous rewilding. There is nothing wild about a fenced industrial array containing domestic livestock on an engineered seed mix. Rather, it represents something far more profound, a fundamental rethinking of how we manage infrastructure land. Across Canada, vast expanses of utility rights-of-way, roadside corridors, and fenced industrial verges have historically been treated as sterile maintenance liabilities, kept barren through diesel mowers and chemical herbicides. As thousands of hectares of clean energy infrastructure are deployed across the country to meet our future power demands, what happens beneath that steel infrastructure is entirely a matter of deliberate ecological design. If we seed industrial turf and mow it with heavy equipment, we get an ecological desert. But if we seed diverse native pollinator mixes and manage targeted livestock grazing, we build living soil, triple insect biomass, restore native bee populations, and support adjacent working farms. The clean power generation was always going to be built. The living ecosystem underneath was a conscious choice. The Canadian landscape was never dead. It was merely waiting for us to pay attention.